Okay, hi everyone. My name is Shireen Sohrabi, and today, together with Octavian Yudra and Michael Katz, we'll be presenting a tutorial on AI planning, theory, and practice. Now, a few things before we get started. If you can, please write down your area of expertise in the chat on the right-hand side, so we have some rough ideas about your background. Now, if you have questions, please use the raise hand feature to ask your question, and everybody is muted on entry. So please unmute yourself to ask your question and then mute yourself afterward. And also know that we are recording this session, as Michael wrote down in chat. You can write questions in chat as well, but as we're presenting, we may or may not be able to get to those questions. Also, so if you want those questions to be in the recording, then please raise your hand in order to ask your question. I think that's it. So, I also want to say that we do encourage questions. So even though for some parts of the tutorial, we're going to be showing pre-recorded video, do not hesitate to ask questions. It's very easy to stop the video recording and get to your question. Any questions before we get started? No. Okay. All righty, so let's get going. Now, before we get started, we would like to acknowledge and thank our past and present collaborators. Subset of them are shown here. So what is AI planning? AI planning is a long-standing sub-area of AI since the 60s. Planning sits well with autonomous systems and started with robots. When autonomous systems has to achieve something, it has to plan for it ahead of time. Now, this is a picture of Shaky the robot, which was the first mobile robot with the ability to perceive and reason about its surroundings. This was the subject of SRI's Artificial Intelligence Center research from 1966 to 1972. Shaky could perform tasks that required planning, move planning, and the rearranging of simple objects. The robot greatly influenced modern robotics and AI techniques. So planning is about finding a procedural course of action for a declarative described system to reach its goal while optimizing overall performance measures. For realistic domains, the space of possible plans is very large, so optimization is key. Also important is identifying a good quality plan or the top quality plan, or finding a set of possibly ranked plans. So the basic planning problem goes as follows. Given a description of possible initial state of the board, desired goals, a set of possible actions, and you want to synthesize a plan that's guaranteed to generate the state which contains the desired goals. The simplest example that helped ground the basic terminology is the logistics example. You have an initial state location. You have a set of transportation vehicles, trucks, aircrafts, cars, as well as a set of packages. You have to deliver the packages, that's your goal state. What you get as an output of a planner is a sequence of actions that need to take place in order to achieve the goal state. You may also get a set of alternative plans that you want to explore. Now, I want to mention that much has gone into AI planning research, and AI planning is a very active area of research. Now, there are many applications that are examples of use of AI planning. Here are 4 such applications at IBM. Left top, this is the healthcare setting where the objective is to help users, nurses, physicians in early detection of health complications in the ICU setting. Top right, this is the V3WA system, a goal-oriented conversational agent that uses automated planning. Down left, this is the risk management setting where the objective is to assist financial organizations in identifying and managing emerging risks. Down right is the automated machine learning setting, where the objective is to automatically generate machine learning pipelines. Now, there are many common things between these applications. First is the existence of domain knowledge. There are domain experts who can provide the necessary domain knowledge. For example, the type of knowledge for the healthcare setting can be provided by doctors, or there are books written on the subject. Similarly, for the scenario planning, there could be lots of articles regarding the cause and effects that can be explored. Second, people want more than one plan, either for explanation purposes or in the case of plan failures, or in general, wanting to have a better sense of what is possible. In some settings, they will want to have a diverse set of plans, and in some settings, top high quality plans, and in some, diverse but bounded quality plans. Third, humans are involved beyond just providing the knowledge. We have humans that interact with the tool. They need to validate, like what they see. They need the solution visualized and explainable to them. They can dislike or like some solutions more than the others, and there should be a way of indicating that. Now, of course, there are challenges as well. Modeling is an important aspect of use and adaptation of AI planning. Modeling is about how to drive the planning problem in order to use the planning tools. Theory, how to compute a solution to a problem, what planning tools to use. And in some cases, you can use the planners that are available, and in some cases, you end up creating a new planning theory and tool that were motivated by this particular problem or application, but can be used in other application settings. And I'll give examples of those later in the talk. Now, to motivate this talk further, I'll briefly drill down on one of the applications, that is the left down project. That's the scenario planning problem, that application. So what is scenario planning? Scenario planning is a commonly used enterprise risk management technique facilitating decision makers in formulating long-term plans by considering multiple alternative futures. It's typically a manual, highly labor-intensive process that involves dozens of experts and hundreds to thousands of person hours. As a result, only a few scenarios can be constructed by humans. Also, bias can be introduced. So, for example, high-impact, low-likelihood events could be overlooked. So we developed a tool that's called SPA, which is a mature research asset at IBM. This is available as an open service for non-commercial use. Now, with SPA, we see reduction in time for building scenarios from months to hours. We see exploration of orders of magnitudes more scenarios that are humanly possible. And in fact, one of SPA's clients says, and I quote, SPA is 30 times faster in time to generate a dynamic risk model and first scenario, and 3,000 times faster in time to generate the second scenario and each subsequent scenario. Now, this is comparison to a human expert. So in the solution, we use NLU to automatically construct the model needed for planning. And this is the domain knowledge that's needed for AI planning, and that's learned automatically. We use AI planning to explore the possible space of scenarios, and that allows us automatically to generate lots of scenarios. And then we choose the relevant scenarios to present to the user. So why AI planning is important? Well, AI planning applications are everywhere. Many examples are shown here: dialogue, cybersecurity, transportation, logistics, IT, and so on. And many companies have understood the value of AI planning and use it in their offerings. So for example, NASA uses AI planning in Mars rover, Schlumberger uses AI planning in automating the drilling process, and IBM uses it in many applications, as I mentioned before. And note that several of these applications are not your typical initial state goal classical planning problems, but planning is nevertheless used. And the key there is this transformation or compilation step that enables the use of planning in those settings. Now, how to spot a planning problem? AI planning can help when your problem can be described in a declarative way, or you have domain knowledge that should not be ignored, or when you have pure learning techniques that are difficult to use either because there is a structure of the problem that cannot be learned by training, or that there is little to no available training data. Also, you can use planning if you want to be able to explain a particular course of action that the system takes, and that you want to leverage the existing relationship between a problem that's similar to yours to AI planning. And I'll talk more about these challenges in the modeling section of this tutorial. Now, a common framework that we adopt for the use of AI planning is as follows. As I mentioned before, we have domain knowledge, and the first step is to create a planning model. Now, that can be elicited or learned. Here, we need to somehow address the modeling challenge, which is any gap between identifying that you have a planning problem at hand that you can use a planner to compute its solution, to specifying a planning problem in a language such as PDDL in order to use a planner to compute a solution to the original problem. Then we need to run the appropriate planner to solve it. Find plans, sometimes lots of plans, and sometimes we need to create planners that are suitable for our task and are motivated by the problem we face. And in fact, we have worked on a number of different planners such as top K planning, top quality planning, diverse planning, and so on. All of these are motivated by the applications we face and yet are not domain dependent. That is, we made these planners available and the tools can be used by others. Then we need to do post-processing to translate the solution into a solution for the problem of interest and then inspect the solution. This can be done by the users of the application, which can be different from the domain experts. And oftentimes, you may need to adjust the model through feedback and start again. One of the things you get for free with AI planning is that the plans are very much accessible and understandable by humans with perhaps just a good UI interface. So once the users view the plans, they can give feedback to the system and the models can be adjusted accordingly. Now, having this framework in mind, let's talk about the Scenario Planning Advisor, or SPA, in a little bit more detail. So first, how do you know it's a planning problem? Well, we characterize the scenario planning problem for enterprise risk through its corresponding plan recognition problem. Then we use plan recognition as planning technique, which is established relationship between plan recognition and AI planning. This would allow us to use AI planning to generate scenarios. Now, in terms of modeling, we translate the domain knowledge into an AI planning task. And more recently, we automatically extract and use these causal models that form the AI planning task. We then use top K planning to generate a set of top K quality plans, which would then get clustered into 3 to 5 scenarios to show to the user. We can use diverse planning or top quality planning to generate multiple plans as well. The users are able to provide their feedback and modify the model if needed based on the user's feedback. So naturally, here's the plan for this tutorial. First, Michael will talk about the theory, and then I'll talk about the modeling challenge, and then Octavian will cover the tooling. I would like to mention that Octavian will run a hands-on session that will cover end-to-end use of AI planning within the automated pipeline generation application. Okay, so that concludes the introduction of the tutorial. Before we go on to the next section, are there any questions? Okay, I don't see any questions. Okay, Michael? Okay, please go ahead. Michael, we are not seeing your screen. And you are muted.
Apologies, I had to get out of the full screen in order to unmute myself.
Yes, we can see your screen and we can hear you.
Wonderful. So, okay, so this is the second part of this tutorial. My name is Michael Katz. And in this part, I will give a concise introduction to the theory of AI planning. And please feel free to stop me at any point and ask questions. I would like it to be as interactive as possible. So I'm not sure whether I will see raised hands. So maybe I will ask Shirin to.
I will do that. I will monitor and let you know. Yes, yes.
Okay, so let's go. So as every presentation on AI planning starts with what AI planning is actually about. So what is AI planning? This is a version that I like. So to quote a colleague, planning is the art and practice of thinking before acting. And to be able to choose a course of action that is most beneficial to achieve your own goals. So essentially, planning is the problem of action selection. There are many areas in computer science that deal with the problem of action selection. The existing approaches can be partitioned into three main ones. The first one is specifying the control programmatically. The second one would be learning the control from experience, and that's a popular one. And the third one would be deriving the control automatically from a declarative model. Planning belongs to the third category, and it deals with producing the behavior from the model by solving the model. We can say that planning is a model-based approach to action selection. You might have heard of other model-based approaches in computer science in general and in AI in particular, such as Boolean satisfiability, constraint satisfaction or optimization, answer set programming, and mixed integer programming, and others as well. So what is the planning model? Going a little bit into details here, it is a tuple of following 6 elements. The first is the finite set of states S. One of these states is called the initial state. Some non-empty subset of these states are called goal states. And a finite set of actions with a subset of applicable actions defined for each state is also given. And the deterministic transition function maps a state S and an applicable action into a resulting state. Finally, the last component is each transition has an associated non-negative action cost. Right, so solutions here are sequences of applicable actions that start at the initial state and add at some goal state. And going beyond classical planning, relaxing the assumptions that I marked here in blue result in more general models, such as, for example, planning with preferences of soft goals when the hard goals assumption is relaxed. Conformal planning and contingent planning deal with partial knowledge about the initial state. Relaxing assumptions about deterministic action outcomes will result in non-deterministic or probabilistic planning. And relaxing an assumption about observability in general will takes us in the realm of partially observable planning. Any questions so far?
No questions.
Okay. So in order to be able to compactly represent those models, we use planning languages. And probably the simplest one and the most common, the most commonly known is STRIPS, which stands for Stanford Research Institute Problem Solver. So Shirin mentioned the Shaky robot and that SRI team that worked on that robot, and that's the same team that came up with that language and an algorithm that I will talk about later. So in STRIPS, the planning problem is given as a tuple of 5 elements. The first one is a set of atoms or Boolean variables. The second element is a set of operators or actions, each of the form of add, delete, and pre. Each of these are a subset of atoms. The third element is a non-negative operator cost or action cost, that gives a non-negative value for each action. The initial state is just a subset of atoms, and the goal description is also a subset of atoms. And a plan here for strips planning task is a sequence of action mapping the initial state into some state that is consistent with G. And consistency here means that the state is a superset of G. Okay. So given a strips planning task, we can define the model as follows. The states S are just all possible subsets of F. The initial state S0 is I, one of those subsets. The goal states S are all states that are supersets of G. The actions in AS are operators in O such that the precondition is included in a state. And the next state is generated by taking the state, removing the set of delete effects, and adding the set of add effects. And you end up with a subset of atoms again, right? So actions are just action costs, sorry, or transition costs are just set by action costs, right? So all transitions that belong to the same action will get the same cost. And the solutions to the planning model are exactly the solutions for the planning task. Okay, so by now you must be wondering what's the connection between planning and the field that have received a lot of attention in the recent years, namely reinforcement learning, specifically model-based reinforcement learning. While planning and RL were developed separately, there is a tight connection between the two fields. In what follows, I will show how strips planning tasks can be used to define the commonly used models in RL. For the forward model, we need to define the next state. And that is done given the current state in an action, right? So this is done the same way as I just showed you the previous in the previous slide. You take a state, you remove the delete effects, and you add effects. And the only difference is that it is done only for applicable actions, and if for non-applicable actions, it's just a self loop. For the backward or reverse model, we regress an action in a state by removing the add effects and adding preconditions. This is only valid for actions whose delete effects don't appear in the state. For inverse model, we can find an action whose preconditions are included in SI and a plan which would result in SI plus 1. That can be done just by going over all actions in A of S, or all applicable actions. The rewards they approximate the negative of the true optimal cost of reaching the goal from the state, and the transition rewards can be then approximated by difference between the cost estimates for the two states. For the sake of simplicity, we don't show the non-deterministic setting here. Clearly, a more informative model is a mixed blessing. It's not easy to obtain, as you will see in the next part of the tutorial. However, it clearly pays off to have it. And in the next slides, I will show what can be done when we have the planning model. So having established the model, we can think about the questions we might want to ask, or the computational problems that we want to solve. The first one is cost optimal planning, the problem of finding a sequence of actions or a plan that minimizes the summed action cost. Next, in satisficing planning, we want to find any plan improving the plan cost as much as possible. In agile planning, we care only about how quickly a plan can found, ignoring completely its quality. For top-K planning, basically top-K planning generalizes the cost optimal planning, requiring to find K plans of top cost instead of one. In top quality planning, we search for all plans possibly modeled with some equivalence criteria up to a certain cost. Diverse planning deals with both plan quality and pairwise diversity, defining a variety of computational problems, considering satisfying bounded or optimal solutions on any of the two axes. Now that we have defined the computational problems, we need to ask ourselves how difficult are these problems. Plans correspond to paths in the transition graph of the planning problem. And we know that finding even an optimal plan in a graph can be done efficiently in polynomial time. But polynomial in what? The typical number of nodes in the transition graph is huge, and constructing it is not feasible in practice, even for relatively small problems. Planning algorithms work with the planning task representation in strips and measure the complexity in terms of what that representation size. Even for the simplest computational problem of agile classical planning, when you just need to find any solution with no requirements on its quality, the complexity is p-space complete. This is due to the fact that the plans can be exponentially long, exponentially in the strip size. You can think of something like towers of Hanoi or Sokoban, for example. So planning algorithms can solve these problems efficiently because they avoid constructing the transition graph. Any questions so far? Yes, no? So having established what planning problems are, let's look at the methods developed over the years for solving these problems. The first one is strips algorithm, which keeps a stack of goal facts, finds an action that achieves the top fact in the stack, removes that fact from the stack, and instead adds the precondition of that action. Partial order causal link planning performs a search in the space of partial plans. Graph plan constructs a graph in a forward manner that encodes all possible parallel plans up to a given bound, and then performs a backward search in the constructed graph. SAT plan takes a different approach. It sets a bound on setting a bound on a plan length makes this the planning problem NP complete instead of p-space complete. Then it can be cast as a different computational problem. For example, Boolean satisfiability. And SAT solvers can be used to solve the new problem. So what can be done is basically you can gradually increase the bound until you find a solution. All these problems assume a relatively small planning problem given, and they don't really scale to larger problems. The last two approaches are currently the best performing ones. First, informed search, also known as a heuristic search, performs a forward search ordering nodes using the distance estimates H, automatically extracted from the planning task description. Most of the focus here was on ways to extract informative distance estimates automatically. Since typical search could explore billions of nodes, a lot of the attention was given to computationally efficient ways of deriving such estimates. Last but not least, following the approaches successfully applied to model checking, a so-called symbolic search approach makes the search memory efficient by storing all states at the same distance layer together using decision diagrams. Heuristic and symbolic search are the two dominating approaches to classical planning. Okay, so let's dive in a bit into heuristic search planning. Since it was such a central development, since it was such a central to the development of planning in the last 25 years. The idea behind heuristic search for planning is that search guidance can be automatically extracted from the STRIPS representation of the planning task. The search guidance, often referred to as heuristics, is an approximation of the optimal cost of solving the planning problem, and it is often achieved as the cost of solving some relaxed or simplified version of that problem. The simplest such relaxation can be obtained by simply dropping the delete effects of the actions. Then, the cost of optimally solving the delete-free task is an approximation of the cost of optimally solving the original task. Delete-free planning is simpler than STRIPS planning, with optimal delete-free plan generation being NP-complete, as opposed to P-space complete for STRIPS planning, and non-optimal delete-free plan generation being polynomial, as opposed to P-space complete for STRIPS planning. Many state-of-the-art non-optimal planners still rely on partial delete relaxations or ideas derived from it. I will not go into details of the various methods for approximated distance estimates, but I will show an overview of the 5 families of heuristics. Heuristic can be divided into admissible, meaning given the guarantee of never over-approximating the true optimal plan cost, and non-admissible, which do not provide such a guarantee. Admissible heuristics can be used for optimal planning, while non-admissible cannot. In the next slides, admissible heuristics are marked in blue. The first family of delete, the first family of the heuristics I mentioned is delete relaxations, with H plus being the optimal cost of solving the delete relax problem. Admissible but impractical for classical planning, since it takes exponential time to compute. H max and H add are estimates of H plus, and these talk about H max talks about achieving the most expensive fact, and H add talks about achieving the sum of fact about the sum of fact achievement costs. HFF is probably the most famous heuristic, finding some, and it finds some delete-free plan. HP max is a cost-sharing approximation of H plus, and HSA is a set additive modification of H add. The last two, semi-relaxed and red-black planning heuristics, have gained a lot of attention in the last decade. And they're based on the idea that we can relax only some delete effects and still get a tractable problem. The second family is so-called the critical path heuristics. They generalize H max to account for the most expensive tuple of facts instead of a single fact. These are also admissible, but expensive to compute. And their computation time is exponential in M. So that it doesn't pay off in practice for M greater than 2. In fact, for M equals 2, it's also not really efficient. The third family is abstractions, with multiple ideas developed over the years on how to construct explicit abstractions or define the implicit ones. Next, landmarks are logical formulas that must be true at some point along any plan. Some landmarks can be efficiently pre-computed, and the information about their achievement status can be used as a heuristic estimate. Other methods, like the famous LM-cut heuristic, compute landmarks on the fly. Last but not least, potential heuristics define some state features and compute weights for these features. An estimate of a state is the sum of weights over the features that hold in that state. In addition to heuristic estimates, search pruning techniques can significantly speed up the search. Similarly to heuristics, these techniques are also automatically derived from the planning task description in strips. Partial order reduction comes to compensate for the need to explore different orders of applying actions, even if there is no dependence between them, and they can be executed in parallel. Structural symmetries try to capture the structural similarity within the planning task, such as similar objects, map symmetry, etc. Novelty tries to reduce the accidental complexity of the planning task, defining a series of simplified searches. Each of these techniques can lead to exponential reduction in the search space. While partial order reduction and structural symmetries are mostly used for cost-optimal planning, novelty pruning is used for satisficing planning. Any questions so far?
Yeah, I don't see any questions.
Okay, let's continue. I hope that by now I have given you some idea about the amount of various methods for solving planning tasks. Each of these, as well as various combinations, have been implemented as domain-independent planners. Domain independence here means that these planners are agnostic to the source of the actual problem at hand and can solve any planning problem described in the planning language. To be able to perform an independent comparison of these planners and to facilitate the development of planning systems, a planning competition was established. The first international planning competition, or APC for short, was established in 1998 and was run as a biannual event since then. Well, almost biannual, as you can see. The most recent APC happened in 2018, and the next might happen in 2022, if someone will actually step up and organize it. One of the major outcomes in the APC was the development of the unified language, PDDL, to be used as an input to all planners. You will see the examples of PDDL in the next part. The competition features multiple tracks for deterministic planning, non-deterministic, probabilistic planning, temporal planning, or learning track where domain-independent solutions can be developed based on smaller instances of the same domain. Two recent tracks are on solvability, where the task should be proved as solvable, and HTM planning, where a richer description of the planning task can be given. Many tracks have multiple subtracks. For example, deterministic track has cost-optimal, cost-bounded, satisfies, and agile subtracks, each with its own evaluation criteria. Planners that compete in the same subtrack solve the same computational problem and can be compared to each other. The rules of competition are very simple. You submit a planner. This planner should be able to consume a PDDL as an input and output a plan. Once the submissions are closed, the organizers choose a set of domains and instances and run all the submitted planners. So you never see the PDDLs or the input planning tasks, the domains that your planner will run on. The winners, according to the pre-specified criteria, are usually announced during the award ceremony of that year's ICAPS conference. The competitions were an enormous drive for the research in planning for the last 20+ years. Many ideas were developed and first exposed at APC in a planner, but also the competitions forces people to invest into efficient implementation and make their code usable by others. Some of the top performers of the past competitions are Fast Downward Stone Soup, Simba Star, Delphi for cost optimal planning, Llama, Ibacop, Mercury, Fast Downward Stone Soup, and Labsk dual breadth first with search for satisfying, Prost and random bandits for probabilistic, and yet another heuristic search planner and temporal fast downward for temporal planning. Most of these planners are implemented on top of the following planning systems, some of which are still being actively developed. The first one is well-known Fast Forward or FF. It implements a classical satisfying planner, but based on that, on FF, there are numeric planners, conformant planners, contingent planners developed as well. The second one is Fast Downward. It's a framework for implementing classical cost-optimal, satisfying, agile, or cost-bounded planners. But the variants built on top of Fast Downward include oversubscription planning, fully observable non-deterministic planning, probabilistic planning, and temporal planning. I just want to note that most of the planners submitted, the vast majority of the planners submitted at the last IPCs are based on Fast Downward. Lightweight Automatic Planning Toolkit, or LAPT, is a toolkit for classical cost-optimal, satisfying, and agile planners. LPG is a planner for that implements search in the space of partial plans, and it implements a classical satisfying, but also numeric, temporal, and diverse planners. SHOP2 is a well-known HTN planner, and Optic is a temporal planner, which actually hasn't competed in any competitions as far as I know, but it's pretty well known nonetheless. And there are lots of other planning toolkits and systems that I did not mention here. Going beyond IPC planners, there are major efforts in the planning community to make the existing tools easy to use. Some of these efforts include the development of a planning service that captures planners for the most popular formalisms and computational problems, and this was done by our group. This service is available as a source code and as a Docker image, and it's easily deployable either locally or on the cloud. Other efforts are planning.domains, including a restricted version of a deployed planning service for agile planning, and it's a very restricted planner in the cloud that can solve your problem if it's solvable in 10 seconds. But you can play around with it, and it has an editor implemented, and it's very easy to use to start to play around with your tasks. Others include the forbid iterative collection of planners for top K, top quality, and diverse planning. Top K, top quality, and diverse are not participating at IPCs at this moment, and there are just a few planners that support top K or top quality or diverse planning. And most of these planners were developed by our group. Well, for top K and the top quality. For diverse planning, there are other planners available. So OSP planners, which solve a slightly different problem. So oversubscription planning deals with finding sequences of actions of bounded cost that achieve states of as high utility as possible, which is maybe more similar to the reinforcement learning side. fully observable non-deterministic planner PRP as well is a very useful source of very useful planner to have. And finally, a Piper plan, which is a lightweight Python-based planner developed for educational purposes. And it's also something that is easy to use if you are coding in Python and you want to run this planner. Last, I would like to mention the community Slack workspace, where you can get help with any issue that you have from planning researchers of any level of seniority. ACAP's website is a good source of information as well. In addition, we have a community GitHub with some of the projects developed jointly by many community members. One of these projects is PlanUtils, providing singularity-based runnable images and running instructions. And you will see a use of PlanUtils in the next parts of the tutorial. Also, there is a planning wiki, which is an initial effort, but also a good source of information. In particular, it includes the list of planners, and this is a relatively updated list of planners that are out there. The links to tools and planners mentioned in the presentation can be found at the tutorial webpage, and you can follow the QR code to get there. And since I didn't have any questions during the presentation, I assume that you kept everything for the end, and I will take your questions now. Okay, we have a lot of time. The next presentation will start in 43 minutes, and we can either have some questions and discussions, or we can take a long break. I'm so glad that I made it so clear for everyone. I will leave this.
Michael, we can't hear you. I don't know, got disconnected. We still can't hear you. Just wanted to say that, as Michael said, that the next session will start at 11:30. So the 11:30 Eastern time. So that's in roughly about less than 45 minutes.
I hope you can hear me now.
Yes, we can hear you now. Yes.
Okay. I don't know. I mean, can you hear me now?
Yes, we can hear you now. Yes.
Okay. So I hope that you could hear me until the end of the presentation, because this device just told me that it's disconnected. Did you hear me at the end?
Yeah. Yes.
Okay, great. So I will put the last slide presented during the break, but I would really encourage you to ask questions and get some discussion going on. You have a lot of time. Have 40 minutes until the next session. Okay, then let's take a break, and you can always go to the website of this tutorial and find our information and contact us. and we are happy to talk to anyone and ask questions, answer questions. Sorry. So let me share that slide again, and see you in 40 minutes.
Okay, so let's go to the second part of the tutorial, the modeling section. Okay, welcome back. Next, we'll be covering the modeling part. As I said, we consider any gap between identifying that you have a planning problem at hand, that you can use a planner to compute a solution, and specifying a planning problem in a language such as PDDL in order to use a planner to compute a solution to the original problem to be a modeling challenge. This requires obtaining the knowledge, representing the knowledge, extracting and possibly learning it, validating it, as well as updating and enhancing it. So some modeling challenges are you often need to transform the original problem to a problem with known or easier to compute solution. This is the same line of work as it's done in terms of transformation or compilation steps that are done to solve a hard problem using a relatively easier and with known solution problem. Second, access to domain experts familiar with input to planners, for example, PDDL, is rare. Furthermore, any form of knowledge is practically guaranteed to be incomplete and often inconsistent. Even human validation can be ambiguous. Finally, current state-of-the-art learning approaches may not scale and may have assumptions that may not hold for the practical setting. Further, the learned knowledge may not be consumable. Now, let's drill down more on the first challenge on establishing a relationship to AI planning. Sometimes it's trivial to write down a planning model, and sometimes it's not. And you need to find a relationship to an existing problem with established connection to AI planning problem. We call this a planning problem in disguise. So, for example, you have to define the original problem, and then you have to make a correspondence to AI planning. So you need to then reduce it to a problem in which an established relationship to AI planning exists. This allows you to use AI planning tools to compute a solution, and then you can post-process the results and compute solutions to the original problem. So, for example, in the case of scenario planning, an SPA, you need to first define the scenario planning problem. Then you make a correspondence between scenario planning problem and the plan recognition problem. That is, we link the relationship between the different forces such as technology, currency, social order, corruption, and natural disaster to AI planning task. The drivers that the users select in order to perform their what-if analysis are the observations. The implications, the drivers that have a special importance to the users are the goals. We then leverage the existing relationship between plan recognition and AI planning to compute the solution to the original problem. Note that we sometimes have to extend the established relationships in a number of different directions. So for plan recognition as planning, we had to extend it to consider observations that are over fluence or properties of states, and that they can be unreliable. Not all of them are explainable. I want to point out that there are several established relationships to AI planning that's often explored. For example, finding excuses, or diagnosis as planning, or explanation generation, in addition to plan recognition as planning. And they, in turn, help with other problems such as hypothesis generation and exploration, future state projection, multi-agent plan recognition, as well as scenario planning. Now, in addition, I want to mention some other commonly used compilation techniques that can be used when it comes to the modeling challenge. For example, we have compiling away soft goals. This will let you use any classical planner to obtain a solution for a planning problem with soft goals or simple preferences. Also, we can translate HTN problems into classical planning problems. And this lets you use classical planners or heuristic search in particular to find solutions for an HTN planning problem. Now, an example application where we have used the translation from HTN planning to classical planning as well as compile soft goals away is the automation of machine learning pipeline generation. That is the write down application on this slide. Now, the problem is that the space of possible pipelines is huge. Humans can explore only a tiny portion of it, and humans can be biased toward pipelines that they are already familiar with. And in terms of benefit, you get to generate pipelines of high accuracy automatically and also reduce the need for human data scientists. In terms of solutions, our solution uses planning tools for exploring the space of possible pipelines defined with the use of regular grammars. Now let me tell you a little bit more about that. Now, given a data science grammar, we transform it to HTM planning problem, then to classical planning problem. We integrate user-defined constraints, turning the classical planning model to classical problem with soft goals. And then we compile these soft goals away, obtaining again a classical planning model. We then can use top quality and diverse planning to generate multiple plans, each post-processed into a machine learning pipeline. The pipelines are then trained on specific data sets, and their accuracy feedback is used to adopt the planning model. In order to focus the exploration of valid pipelines, we allow for specifying preferred non-terminal and terminal symbols. The non-terminal symbols correspond to the rules of the grammar and allow to prefer, for instance, using a particular family of algorithms. Choosing a terminal symbols allow for preferring a specific algorithm or even a specific value for a hyperparameter. The preferences are then translated to soft goals, which are added to the classical planning problem instance. Then the soft goals are compiled away using the transformation proposed by Koller and Daphne, giving us again a classical planning problem instance. I want to mention that in the third part of the tutorial, Octavian will cover this application in more detail. Okay, now let's talk about the planning language, that is how to represent the domain knowledge. In this example, I'm going to be showing language written in PDDL, or Planning Domain Definition Language. There are other languages as well, such as HDDL, language to describe hierarchical planning problem, or RDDL, that's used for probabilistic planning. We'll just here talk about PDDL. Recall that Michael in the theory section talked about the strips. language to define a planning problem. STRIPS is a subset of ADL. And PDDL is the standard input language for planners that originated from the International Planning Competition. You can define both types of problems, STRIPS as well as ADL, in PDDL. Now in PDDL, you define two files. That is a domain file, that's the left picture, and the problem file that's shown in the middle. The domain file includes description of the actions, a list of predicates, types if any. Problem includes the initial state, the goal state, and the objects. Here's an example of a mechanic elevator domain. The domain file has actions for boarding a passenger at a particular floor, departing a passenger, as well as elevator going up or down. The initial state includes information about passengers, locations, floor numbers, the original and destination location of a passenger, and the original floor of the elevator, as well as the predicates to define the relationship between the floors. The goal is to serve the passengers. Normally, the domain file is fixed, while the problem file can vary in difficulty. And here there are 4 passengers and 7 floors, and normally you have a generator that generates many different problems for the same domain. And finally, you see the plan on the right. That's a sequence of actions that's automatically generated by the planner. I would like to point out that there are many examples of modeling tools that have been developed, and here I'm just showing some of these examples that were developed at IBM, but there are many others. These tools are developed because oftentimes when you interact with a domain expert, they will not be familiar with PDDL, but they would like to be able to express the knowledge, and you want to be able to obtain the domain knowledge somehow. I also like to point out that these languages and modeling tools are just proxies for obtaining the domain knowledge. Once information is obtained from experts, it's automatically translated into PDDL, which is the input to the planners. Next, I'll go over some of these modeling tools. First, recall the examples that I showed in the intro. So these are the 4 potential applications of planning. And now I want to drill down more on the top left application, which is called the hypothesis generation problem. Here is a healthcare setting for the hypothesis generation problem. There are other settings such as malware detection, and Octavian in the third part of the tutorial will go over that example in a little bit more detail. But in terms of the healthcare setting, here it goes. So you have a patient in typical ICU setting that's connected to several monitoring devices that measure different physiological attributes such as the patient's blood pressure, heart rate, and temperature. The analysis of these raw streams of data results in semantically meaningful observations about the patient. For example, given the patient's heart rate, their respiration rate, and their body temperature, which are measured continuously, and also their white blood cell counts obtained from blood analysis, you get this some score. It's called Sears score. It's between 0 and 4 that can be computed as a meaningful observation about the patient's health. Observations can also include other measurements provided by physicians, such as their assessment of patient health or lab results. Note that the observations are partially observable and they can be noisy. Now, a simple model that represents the transitions in healthcare application are shown here. Nodes are states, and the observations that we saw earlier in the previous slide are associated with these states. So the patient is initially admitted, then they can be in low or high risk state, and things can progress to pre-complications and other states. Note some of them appear in more than one state, which is called ambiguous. For example, SIRS-3 can be associated with both a high risk state as well as the infection state. These observations can also be unreliable. They can be noisy, missing, or incomplete. Therefore, some observations may be left unexplained by the model. Now, in order to capture the knowledge, we proposed a modeling language named LTS++. So it's based on Labeled Transition System, or LTS. And we built an integrated deployment environment around it. Here's a screenshot of the tool. And here's the LTS plus representation of the same healthcare model that I showed in the previous slide. Now, I won't go through any additional detail, but basically I want to mention that you can specify states, you can specify class types, you can specify a relationship between observations and state in this LTS plus model. Now, everything that you describe in LTS++ is then eventually, translated automatically into PDDL. To do that, we have defined a fixed planning domain for any model that's described in LTS++, but varied the planning instance based on the given LTS++ model. And here's the planning domain. It contains 6 actions: explain observation, discarding observation, state transition, entering a good or bad state, or allowing a state to be unobserved. And here's an example of a problem file that captures the exact knowledge of what I showed in the previous slide in terms of the different transitions of states. And here's an example of an output of the planner. Basically, this is a screenshot of the LTS++ system. The input, the trace, is given in green. That's the sequence OHH1, OSIRS 0, and OSIRS 2. This is a sequence of observations that you want to join the hypothesis for. The state transition, or some small subset of it, is shown on the right. The PDDL problem file is created automatically, as I mentioned before. Then we run the TopK planner to compute a set of plans. And here, what we are showing here is just the top 4 plans. This is after the post-processing in order to be able to visualize the plan, or now the hypothesis. Each hypothesis is shown as a sequence of states matched to observed event sequence. The first 3 hypotheses explain all observations. The last one doesn't explain the first observation, that's shown in purple. A lot more can be said on this application and LTS++. I would just say that while I showed the healthcare example, we've worked on a number of different applications within this framework. And in particular, as I said before, Octavian will talk about the malware detection application in the tools section of this tutorial. Next, I will talk about the scenario planning application in a little bit more detail with respect to the domain knowledge, or obtaining the domain knowledge. So recall that the scenario planning problem is about identifying and managing emerging risks. It's a commonly used practice that many organizations use to develop their long-term plans. Scenario planning involves analyzing the relationship between forces such as social, technical, economical, environmental, and political trends in order to explain the current situation, in addition to providing insights about the future. One of the main tasks, in addition to the automation, is gathering the domain knowledge from experts. Our first attempt was to use mind maps to capture this knowledge. So rather than specifying the domain knowledge in PDDL, or in planning terms, which are hard to do for domain experts, we created a way for experts to encode their model using mind maps. And then we automatically translated these mind maps into PDDL. So here's an example of 2 mind maps. You have the center concept, which is, for example, currency depreciation against US dollar, or decrease in price of commodity. And then you have nodes on the left. These are causes, and you also have nodes on the right, which are
called the consequences. The way to read this is, for example, high inflation may lead to currency depreciation against the US dollar, which may lead to increase in taxes. Now, we allow for customization of mind maps, and that is elicited using generated questionnaire that requests likelihood and impact for selected cause and effect pairs. So we started with mind maps as a way to capture the domain knowledge. We worked with domain experts that provided this knowledge, and during this process we realized that for a reasonably sized set of drivers, domain experts can take days to weeks to express their causal knowledge. Writing the domain knowledge in mind maps helps to some extent, but it can be impractical, especially with regard to maintaining that knowledge. On the other hand, causal knowledge can be extracted from experts' authoritative documents using natural language understanding, or NLU, order of magnitude faster. So best solution to date is as follows. We use learning-based natural language understanding techniques to identify risk drivers and extract causal pairs. We use AI question answering for automated reading comprehension by asking questions such as what causes X. This is best done using authoritative documents that are rich in causal context, for example 10K reports or NATO SFAs. And we will ask open-ended questions based on seed set of drivers, and this will result in potentially discovering new candidates and helps with bootstrapping. For causal extraction in support of planning model generation, we had a few options. For SPA, we created CFAS, causal extraction from authoritative sources. CFAS uses AI question answering to answer causal questions about risk drivers. It relies on relatively a small set of authoritative documents, for example, US Securities and Exchange Commission's Form 10K, each of which is a comprehensive report filed annually by public companies about their financial performance. Especially item 1A, risk factors, providing detailed coverage of company and industry financial risk. Also, NATO Strategic Foresight Analyst documents is a periodic analysis of global risk in all areas of risk, including, for example, social, political, or environmental and economic risks. CFAS processes all input documents, asking for each paragraph of each document and for each known risk driver D, what causes D and what does D cause. Next, I want to drill down more on the top right application, planning for dialogue. So, what's the current state of conversational agents today? The market size is big. There's lots of money involved. There's a lot of focus directed toward dialogue agents. The potential saving is also substantial. And we know the current players: Google, IBM, Apple, Amazon, and Microsoft. We also know that there are some or many deployed agents that have really undesirable behaviors. So, for example, on the left is the state-of-the-art in a believable agent that's using ML or DL. And this is an image of an RNN approach. The agent says, hello, how can I help you? And the user says, I'd like a trip to Toronto, please. And the agent says, okay, a trip, where to? And the user says, never mind. Now, the next example is an imaginary great DL approach. And it goes as follows. The agent says, hi, what seems to be an issue? And the user says, all of my emails are gone, help. The agent says, I understand entirely how frustrating this can be. We know exactly what happened and we'll have it resolved in an hour. If you like to check the status, your ticket is number 123. And the user says, that's a relief, thanks. Now, the point here is that the provided information can be useless if it's not connected to an API. So the ticket 123 is either data leakage or could be fabricated. Now, in terms of dialogue as planning, the setting is the multi-turn dialogue or conversations that are goal-oriented and multi-turn. The challenge is scaling up to large dialogue trees. The solution is to not define the dialogue tree, which can be very large, very hard to maintain, but that's done often in the most current system, but to define a mechanism of the domain declaratively via AI planning, and then let the planner generate the tree automatically. Model acquisition, learning, refinement, etc. is also very important in this application. Now, a key difference with imperative design, somebody manually defining a dialogue tree, is that instead of starting with what the user says and then figuring out the different ways of how to react based on the dialogue tree, it becomes, these are the bot's capabilities, these are the different skills and so on, and here are the goals to achieve. So concretely, the bot is on the nodes and the users and environments are the edges or the outcomes. Also want to point out that in this approach, the tri-state variable, the things that are unknown, can be modeled as well. Stateful conversations, patterns like slot filling or confirming things or digression can also be modeled as simple planning constraints. The tool is called D3WA. Here are some screenshots of the tool. With D3WA, you get exponential scale-up, and this scale-up means increased sophistication of dialogue 3 with same size of a specification, and decreased size of a specification for same sophistication of dialogue 3. Now, there's a lot of related work. I have not covered this in this part of the tutorial, but I want to mention them very quickly. This is the list. We have It's Simple, we have PDDL Editor, PDDL in Python, Plan Animation, PDDL plugin for VS Code. There's also a workshop on knowledge engineering for planning and scheduling CAPS that runs every year at ICAPS. Also, there's a book on PDDL titled An Introduction to Planning Domain Definition Language. There's also lots of different approaches and systems that address learning the action model from some input plan traces using variety of different techniques such as MACSAT, Markov logic networks, graphical model estimation, generic algorithms, and finite state machines. Now, in summary, modeling is an important aspect of use and adaptation of AI planning. As we saw, investing in transforming and compilation technique pays off. Lots of different approaches, in particular in applications, do use these compilation and transformation techniques. Also, learning consumable planning models or even enhancing a planning model automatically is very important, as we saw in many real-world applications. Now, this concludes the modeling section of this tutorial, and now we're going to be taking a break. Thanks.
Okay, are there any questions before we go on the break? Audience have been very quiet today. Okay, so now we have a longer break. It's 1 hour. In Eastern time, we'll go, right now is around 12. We'll be back at 1 p.m. So we'll be back in 1 hour. Okay. Thanks, everyone.
Okay. Hi, everyone. Welcome to the last section of today's tutorial, the section on tools and applications. We're going to go over a hands-on example of using planning in a very practical application. The application is machine learning pipeline exploration. The code for it is on GitHub as well. And I've listed here, you have a QR code in case you're using your phone to get to that link. And I've listed here a few tools that we're going to be using. Instructions for installing them are on the GitHub. And I'm going to go over that list a little closer to the hands-on portion. First, I have just a couple of slides illustrating some of the challenges in applying planning in practical applications, in particular this application. And like before, please interrupt me with questions. Okay, so what are some of the biggest challenges of using AI planning in applications, and in particular this ML pipeline exploration application? Well, the first one, and I hope Shirin convinced you of this during the modeling section, is that the planning domain, the stuff that you see in PDDL, for instance, or in HDN representations, is not the application domain. So getting from the application domain, in this case, exploring a large space of machine learning pipelines to the planning formulation of that domain takes some thought. It is not trivial in most cases, and it involves planning experts in most cases in our experience. Then the subsequent challenges in terms of engineering a solution in that space is there are very few integrated tool chains for AI planning. The good news there is that some have appeared that try to integrate more and more tools. So the PDDL editor plugin that I'm using for VS Code, for instance, has a lot of features that are very relevant in terms of debugging planning models and understanding the outputs and syntax highlighting and so on. PlanUtils, on the other hand, is a toolchain that allows you to explore different planners and run them and so on. There are, however, few libraries and frameworks that integrate AI Planner. So if you want to call the AI Planner from code, well, there aren't that many libraries that allow you to do that with ease. And if you look at our GitHub code, you'll see that we actually rely on calling processes in the operating system to run the K-Star Planner, for instance. And then, that K-Star Planner produces JSON output, and then we parse the JSON output and process it, as I'm going to show you in a few minutes. So what does all that lead to is round tripping is cumbersome. So essentially you're starting from an application domain, you do the hard work of mapping it to a planning domain, and then you use this suite of tools, which sometimes are separate and independent. And then you get some output, which are a set of plans, and then you manage to translate that to something that's relevant to your application domain, in this case, machine learning pipelines. And then you have a problem in the machine learning pipelines. And now you have to go all the way back to your original mapping and figure out in which of these steps was the error made, and how can we make changes based on that outcome. So usually when you have processes with many transformations, round tripping from the end result is somewhat cumbersome. But the benefit is, as you'll see at the end, that planning can solve some really hard problems. I'll talk more about this as we get past the hands-on section. So one more slide on pre and post processing, because it's so important, because it's the key. The application domain is not the planning domain. So you have to pre-process kind of your application domain knowledge to turn it into a planning problem, and you have to post-process the plans that you get to turn them into results that are relevant in your application domain. So the way I like to think about this is asking some fundamental questions like the ones you see on the slide. So what's the similarity between your desired output and plans? This is, in a sense, this is starting from the end, but it is driving the problem from your end result. So in this case, we're going to generate machine learning pipelines. And those look remarkable like plans. I mean, there's a branching factor here and there, but if you think about a machine learning pipeline, it's essentially a sequence of in our case, it will be sklearn, estimators, and feature transformers that are applied to a data set to get a prediction out. right? So if you think of those as individual actions, then it is similar to the concept of plans. And a similar question goes at the beginning, based on what you have, how does that map to a planning form? Does that map to a planning formalism? Are you solving essentially a search problem through a planning or planning related space? And then you get into more fine-grained detail. So the elements of the input, and you'll see that in our hands-on, how do we map those to predicates and actions? So for instance, in this case, we're going to start with the grammar, and the kind of terminal tokens will be mapped to actions, and the grammar rules will be mapped to methods in the HTN paradigm. So you need to do that thinking. And then inevitably in these spaces, because you have all these translations, you're going to have what we call maintenance actions in the planning domain. So actions that do not necessarily translate to any output that you see, for instance, in the machine learning pipeline, but have their role in terms of maintaining state and making sure that your output is conformant to whatever input rules you have. So with that being said, this is the kind of thing that I'm going to draw your attention to during the hands-on. So what's the application? The application is automating machine learning pipeline generation. And in particular, we're just going to use very simple pipelines with a very simple grammar, because we have to get through this in 45 to 50 minutes. And we're going to essentially use sklearn transformers and estimators for the purpose of creating ML pipelines. So the problem there is that the space of possible pipelines is huge. If you ever looked at some of these pipelines that are, for instance, in the Kaggle competition, you will see that there are some very creative ways of combining, feature transformers and estimators there, mostly designed by humans, right? And again, humans have a bias towards things that they know. So if you want to explore more broadly, automatically, the space of pipelines that are relevant to a particular problem, then you need some sort of automated technique. Now, why is planning relevant to this particular problem? Well, because you do have some domain knowledge that you want to encode. So sometimes you have either goals. So for instance, a goal would be, what kind of shape of a pipeline do I want? And it's typically a string of transformers followed by some estimator with some potential parallelism. We'll talk about that. Or you have some domain knowledge in terms of the constraints that you want to put on it. So for instance, for this data set, you're going to see me put a constraint that I absolutely want principal component analysis as part of my feature transformation for the particular data set that I'm going to use, right? So planning allows you to do both of those things instead of just exploring basically blindly, generating pipelines blindly without a goal. Furthermore, it allows you to prioritize between these pipelines. So we're going to see that as well as we train a pipeline and to see how accurate it is. And then we feed that back into the planning model to derive new costs and then get better pipelines in the next iteration. So with that being said, Shirin already showed you this diagram, but essentially what we're going to go through in the notebook that I'm about to show is this process. So we're going to start with a data science grammar. And that's going to be in BNF form, and it's going to be very, very simple. So essentially, it's going to specify a space where we have a sequence of transformers and one or more estimators, and with some possible parallelism there, but not much. The grammar is though deceptively simple because it can generate an infinite space of pipelines potentially because it's recursive. And we're going to see that grammars actually match very well this hierarchical task network planning concept. And then, so we're going to use an HTN translator to generate, we're going to translate the grammar to HTN. And then because we need multiple plans and there is no HTN planner that generates multiple plans, we have to go to PDDL because for PDDL, there are planners that can give us multiple plans. And then based on that, we're going to transform the plans to pipelines. We're going to train the pipelines. We're going to execute them, and we're going to see how well they do and how that translates into costs. So last slide before I switch screens. So you have the GitHub there. I'm going to use a number of tools. There's an HTN to PDDL translator. That's that GitHub address, and a K-star planner, which was developed by this group at IBM. And both of these are installed and configured using plan utils. So we're going to call them. You're not going to see plan utils there, but essentially both of them are installed beforehand with plan utils. I'm also going to use the PDDL editor for VS Code because I'm going to show you intermediate output, like what the PDDL looks like, what the HCNs look like, and I wanted some syntax highlighting for that. So with that being said, I am going to bring my other screen here. So I'm hoping right now, can I get a verbal confirmation that you can see my Linux VM?
Yes, we can see it.
All right. So I have a Ubuntu virtual machine here, in which I'm going to run the notebook that is that you can see on the GitHub address. And at the beginning, I'm going to essentially generate a lot of intermediate results, and I'm going to put them all in this directory output. And what I'm going to do as the next step is I'm going to open a VS Code instance on that output so we kind of see the files that are being generated. So I'm going to run this cell by cell. And in the cells that I want to draw your attention to something, I'm going to pause and draw your attention to that. So let me run this cell by cell. So the first thing we're doing here is we're just taking the grammar and putting it into output. So I'm gonna do that. I apologize for that. I should have muted my Slack. And now next, I'm gonna just launch VS Code because I want to see this output in VS Code. So for right now in VS Code, I only have the grammar. So the grammar looks something like this. Essentially, a machine learning pipeline is some sort of directed acyclic graph followed by an estimator. So it's a DAG of feature transforms followed by an estimator. And by the way, what this is generating is a string for something called LaLe, which was developed at IBM, which is a declarative language for creating sklearn and other framework pipelines. And then what I have is essentially the directed acyclic graph is a choice. So I have, I'm sorry, I'm gonna just turn this off completely. Just because it's bothersome. I apologize about that. So, so the direct acyclic graph is essentially a choice of multiple ways of expressing this, and I'm going to show you a graphic very soon. And there is some parallelism. So, for instance, this is a symbol that expresses a sequence in LaLe, and this is a symbol that expresses two parallel branches. So I'm running kind of two things at the same time, and then I'm commingling whatever new columns they generate in the updated data set. So think about kind of creating feature transforms in parallel, and then you're putting the derived features together in the data set before you apply an estimator. And then we have choices of various transformers that are in sklearn and various estimators. So it's as I said, a deceptively simple grammar. The reason I'm saying deceptively is because it's recursive. So as you can see, the DAG itself is defined in terms of a DAG. So you can have an infinite number of transformers generated and followed by, so because the DAG itself can contain an estimator, if you ever looked at the Kaggle machine learning pipelines, you can actually have multiple estimators. So you can have an estimator make a prediction and use that prediction as features for the next estimator, right? That happens fairly often. So you can have multiple of these estimators as a pipeline. Okay, so that's the grammar. That's what I copied. And by the way, in the notebook, I put a bunch of cat commands just so you have all the files there in case you don't want to use VS Code to see the output that way. I'm just going to skip those cells because they essentially print what I'm showing you in VS Code. So if I go a little bit back to the grammar, this is something that a data science expert can tell you. And basically they want their pipelines to have this kind of shape. And as I said, the shape is deceptively simple. But this also matches. So if you remember the hierarchical task network paradigm, it matches that very, very well. So in hierarchical task networks, you have a top level task that you want to accomplish. So say book a flight. And then you have different methods of accomplishing it. You can go through an agency, you can go through Kayak, you can do it all yourself, book the flight, book the hotel, book the rental car if you're talking about booking a trip. So if you think about it, this is the kind of head of the rule is the task. And the different options I have for achieving that rule, think of them as the methods in H10 planning. And then each method has kind of a sequence of other things that happen within, and it's hierarchical. So it decomposes that way. And this is very similar to the structure of a grammar. So A logical step for using planning in this space is to just take this and make a HTN specification out of it. And that's exactly what we do in this next step. You can browse the code at your leisure. I'm not gonna go through it exactly, but essentially what this does, it's generating two files, domain HTN and problem HTN, which are the hierarchical task network specification of that grammar. And the transformation is, not trivial, but if you follow these kind of steps that I described, it's pretty understandable. So you're going to see a lot of symbols here that are not necessarily human readable, but essentially what you're going to see in the domain are a bunch of methods, and the methods correspond to, remember, those choices in the grammar. So I can achieve DAG through a bunch of options, which are these ORs there. So I have a bunch of methods. So I have a bunch of cases for the DAG, for instance, case 1, case 2, case 3, and so on. And it's talking about the subtasks within that case. And then I have individual tasks for every part of the tasks in that case. So for every part of the OR, if I scroll down a little bit to where the tasks are, I apologize about that. So if you look at here we have kind of the actions for the different tasks, right? So think of the grammar as this is your top level task, and this is achieved through three things: DAG, this terminal symbol, and EST. And then DAG in itself has a bunch of methods that correspond to each of these things within the pipes. So each of these big ORs. So that's the domain. That's the translation between the grammar and the domain. So we parse this grammar, and then we generate the HTN translation. And similarly, we generate a problem, but right now the problem in HTN is just a skeleton because we're not done yet with all of that. And one thing I wanted to also show you is kind of a visual representation of that. So, obviously because it's recursive, I can't really fully represent it. But as you can see, this is kind of the big DAG here, and it's recursive because it refers to itself, right? So for instance, you have multiple options of achieving the DAG. You can have this kind of transformer big OR between these transformers. You can have an OR between these transformers followed by another DAG. So you could have another set of transformers there, for instance. Or you can have a set of transformers in parallel with another DAG. This is what these symbols represent. So you have to take all branches between a choice, the TFM, and the DAG. Or you can have one of the estimators in parallel with the DAG, right? So basically use the estimator as a way to derive new features for another estimator. And then all of this has to be followed by at least one estimator at the end, right? So even if you don't have an estimator in your original DAG, there's definitely an estimator at the end because you need to make a prediction. So that's kind of what we generate from the grammar. So we generate the domain and HTN and the problem HTN. Now, as I said, there is a problem with using HTNs for this task. And the problem is I want multiple machine learning pipelines. Now I want to explore this. I don't want these one at a time. However, there are no solvers for HTNs which will give me top plans according to some cost metric, right? So typically this will give me one plan, and then I have to figure out how to exclude that plan from the subsequent result and so on. It's much easier, however, because we developed top K planners to translate HTNs to PDDL, and we're using that work that I put in the that I linked from the slides, that takes an HTN and basically translates it to the PDDL. But before that, I have to set some parameters, and this is what the cell does. So in this cell, I remember I told you that one advantage of using planning is to use constraints. So here, for instance, if I choose just 10 plans, I'm basically just going to get, transformer estimator, transformer estimator, transformer estimator, and in multiple configurations. However, before I do that, that's what we're going to use for training ultimately. But before I do that, I wanted to show you some more complex plans. So for that, I'm actually going to put some constraints here. So I'm going to say, I'm going to force it to have concat somewhere in the output. And I'm also going to force it to use a decision tree classifier somewhere in the output. And I'm going to increase the number of plans to 20. Just to show you a little bit more complex plans. And then we're going to go back to some of the simpler ones. So if you generate the PDDL from that, and if you solve the planning task, then I'm going to, again, go over these in a little more detail on a second run and show them finally. Okay, so we can see some of this, and some of them are pretty complex. So, you know, for instance, it's using a QDA and the standard scalar, and then whatever the derived features are from those are being concatenated, and then on the full data set, it's using a decision tree classifier, right? So again, I only took 20 plans. Usually when you run this in practice, you have to take a lot more, but we have to fit this in 50 minutes. So the idea, I forced it here to kind of have certain things in the plan, like concat and the decision tree classifier. And, you know, they're not, the prefix of that is not always the same, right? But so for instance, sometimes it uses a KNN and the robust scalar. So it's giving me multiple options of how these pipelines with these types of constraints look like. But in order for us to understand what the HTN to PDDL translation is, I'm gonna go back and rerun these and give some simpler pipelines just so we can see the generated PDDL for those. So I'm gonna go back to this and only use PCA as a constraint and limit myself to 10 plans because that's doable in this amount of time we have. And I'm gonna generate the PDDL description. So that will actually generate two files, domain PDDL and problem PDDL, which I'm gonna show you next in output. So hopefully they've been loaded here. There they are. So if you look at the domain now, so what happened is, again, some of these things are not human readable, but you have to translate from that hierarchical task network, which has methods, tasks, and actions for the tasks, to the pure PDDL framework, which has actions with preconditions and effects, right, and predicates. So for that, what this translation does, it generates a number of actions which are maintenance actions, which say, oh, this task has begun, this task has ended, right? To just keep state and make sure that whatever structure of the plans you generate matches those constraints about where the limit, the end starting points and ending points of the tasks and what the constituent tasks could be and what the choices within a task could be in terms of its methods and so on. So you're going to see a lot of these maintenance actions, but if we scroll a little bit down, you're also going to see actions corresponding to kind of the individual elements terminals in the original grammar. So for instance, this is one that's corresponding to the standard scalar terminal in the original grammar, if you remember it. So I'm gonna go back to the original grammar just to see it. So there was a standard scalar there that was a choice here, and this choice was going into another non-terminal here, and that non-terminal was going into the DAG, right? So you're gonna have, domain. So you're gonna have actions that correspond to the terminal as well. With preconditioned effect. And a lot of the preconditioned effects just ensure that the structure of your original grammar is being followed in whatever plans you generate. But you didn't have to write this manually, right? All of this was done through kind of an automated process. We wrote the code for going to HTNs, but then HTN to PDDL, it's publicly available. With that, I also want to show, I also want to pull your attention to this. So PDDL actions have costs, right? Michael mentioned this. And basically in top K planning, you want to give the K plans with a minimal total cost. But remember, the costs are on individual actions, right? So the cost of a plan is the sum of the cost of all the actions in that. And right now we know basically nothing about any of these. How good is standard scalar for this problem as a feature transform? How good is robust scalar? We don't know. So basically they're all 50. It's kind of this thing we chose halfway between 1 and 100. But again, the relative value matters there. We also have some maintenance actions, which have a cost of 1. So maybe I should scroll further down to find one of the. So some have cost 0, but there are some with cost 1. Why do we have things with cost 1? We want to impose that we want to favor the shorter plans. So whenever we advance kind of in the plan to kind of a longer method, we basically penalize that. But right now, we have no idea of how important short plans versus long plans are. So comparatively to the cost of the individual analytics, this is a very, very small cost that we have. But that will penalize, 2-length pipelines versus 3-length pipelines. So 2-length pipelines would win. And then there are maintenance actions with a cost of 0. The reason I'm drawing your attention to this is because the cost will change towards the end, right? Okay, so we generated those PDDLs. By the way, interrupt me at any point with questions. I know I'm going a little fast here. Then we run a planner. And in this case, we run this K-star planner that we developed. And we just call it on that domain PDDL and problem PDDL, which we run in temp so that we can delete them easily afterwards with particular parameters. And by the way, we run this as an external process. So if I copy this and I go to my faithful command line here, right? Okay, this will run just as well if you run the installation steps in our process, and it will create this result JSON, which I'm going to show you in just a second, right? Which has the actions in the individual plans. I'm going to show you this in VS Code in just a second. So basically, I just ran the planner over the generated PDDLs. The planner doesn't care about the PDDLs, what domain they're from, right? It just generates this, and I basically generate this in the first planner call JSON because I'm going to call the planner multiple times. So if I look at the first planner called, there are a bunch of plans here. And by the way, we called it with 50 plans. You might have seen that, although I asked for 10 plans. Why? Because sometimes, although plans are theoretically different, you can achieve the same sequence of pipelines through different paths through the grammar. So while the pipelines are equivalent, the plans are not equivalent because the plans contain all the maintenance actions that tell me, oh, this is the choice we took from the grammar, and this is how we realized it. So although the plans themselves may be different, the resulting pipelines would be equivalent. So that's why we ask for more plans, so we can eliminate duplicates that way in terms of the pipelines that are being generated. But essentially, this tells you, oh, so I'm solving that MM thing in the grammar that you had. So it's a DAG, and then it's followed by so the DAG is it's a TFM. The TFM in particular goes through the WTFM rule, and that goes to PCA. Remember, I asked for PCA. And that flows into an estimator, which in this case is following this rule, GLM, and that basically translates to logistic regression. So if I go back to the grammar, let me find the grammar. So remember, so we went MM, DAG, TFM, WTFM, PCA. So basically it said, well, I'm solving MM, so I need to solve DAG. So to solve DAG, I'm going to take this choice. I'm going to solve TFM. In order to solve TFM, I'm basically going to choose this path. I'm going to solve WTFM. And WTFM means PCA. And by the way, it took this path because I had a constraint that said you have to have PCA somewhere in this flow, right? And these plans that are just two analytics long are better than 3 plans where I had something else followed by PCA and so on because of that cost structure that I talked about. And then this is followed by an estimator, so you can kind of follow the names of the actions in the same way. So this is what we get. And now we come to the part of post-processing. So I got these plans, so now what, right? But remember, all of these rules correspond in the grammar to certain terminal strings. So I can kind of put together the sentence that that matches the grammar right now. So, so essentially, in this next block of code, all I do is I take the actions, and I know that each of those actions corresponded to some sort of terminal or non-terminal node in the grammar. And I basically just create a sentence that the grammar generates through that path that is indicated by the plan that I just showed you. So if I take this, it will generate 10 possible pipelines. And these are all Lale pipelines. You feel free to search for this. If you search for IBM Lale, you'll find a very good tutorial that explains how to programmatically create pipelines for sklearn and other frameworks and test them on all hyperparameter, optimize them and so on. So by the way, I did get a few 3 component ones at the very end, just because it had run out of plans containing PCA that were 2 steps long, right? So it went through kind of all the estimators, and then it said, okay, so now I need to find more plans because I asked for 10 best plans. And again, if I increase that number, you're going to see more and more variations. So if I increase that number by a lot, you're going to see 4 length ones, you're going to see parallel ones, and so on and so forth. So right now I'm just basically displaying each pipeline and showing you what it is. And then what I wanted to do is take one of these pipelines and actually train it. So I'm going to take the first pipeline in that 10 in that set of 10, which is PCA followed by logistic regression. Very simple pipeline. And I chose it on purpose. I chose on purpose some simple examples just so we can walk you through it, right? And what we're gonna do in the next ones is, at this point you can stop. We're not gonna stop here, but at this point you have a number of pipelines and you can actually use them. You can call fit on them. You can train them, right? By calling fit, you can use them to predict, and so on and so forth. So I'm gonna use the famous IRIS dataset that has information about plants. So just showing you what we're loading here, just the last 5, I think it's the first 5 rows. So you have 3 species, if I remember correctly, and you have 4 columns, sepal length, sepal width, petal length, petal width, that you use to predict the species, essentially. So at this point, what I wanna do is train this pipeline that I chose here, the first one, PCA followed by logistic regression. I wanna train it using a hyperparameter optimizer called HyperOpt, using 2 evaluation rounds, scoring based on accuracy. So it's gonna have high accuracy. And I wanna train it and then call it on the test data, essentially. So all I do there is I call fit using the optimizer on the training data, right? So I have the pipeline. The pipeline says it's PCA followed by logistic regression, but I don't really have the best hyperparameters for them at this point. But once I call fit, this will run a number of trials. I'm just going to call it now because it's going to take a little bit. So this will run 20 trials in which it will try to find the best combination of hyperparameters. And then it's going to print the result of calling predict on the tests data set. So the rest of the data set, the 20% that I chose is the test data set. And as you can see, because it's biased for accuracy and this is a very small and very predictive data set, its predictions predicted as the first column, the actual species, the second column, its predictions are perfect, at least for this 20%, right? So, except for one. Okay, so except for this one. But, they're very close to perfect. So essentially at this point, I had a pipeline. I can do this for any of those 20 pipelines I generated, or any of the 100 pipelines if I want to generate more than 20. However, we're not going to stop there. So we want to close the loop. What we want to do is create these pipelines, train a bunch of them, and then see which one is best. And then can we somehow change the planning model to give us better pipelines when we call it next? So think of this as a feedback loop, right? We explore a number of pipelines, we use some training and test data to evaluate them, to call fit and evaluate them. And then we go back and we use that information to re-rank basically the pipeline. So in the top K planner, the next time we call it with exactly the same information, we wanted to give us better pipelines in terms of what we've seen in the last iteration. So if we repeat this loop multiple times, we should get better and better pipelines for this particular problem at least. So that's exactly what I'm gonna do here. So it's gonna take a little bit. So it's, again, we have 10 pipelines. So this is optimizing, the first one, it's optimizing the second one. And it's, and this was the, pipeline that is being optimized. This is its best score. And I don't remember for regression cases, we might be using R2 instead of accuracy, but I would have to verify that in the actual code. So essentially, it's going to run through these 20 rounds for all the 10 plans. In practice, we do this for 100 or even more pipelines. And what we want ultimately is to use these accuracy scores. How accurate were they? So some were more accurate than others. So PCA decision tree classifier was less accurate than PCA quadratic QDA, marginally, but less. So whenever I call this next, I would like to have the one that was better, this one, higher ranked than this one, for instance, right? So I want the PCA followed by QDA to be higher in my ranking strategies than PCA followed by a decision tree. And we're almost there. So once this completes, I'm just going to show you the accuracies of all the pipelines that were computed. And then we're going to go through this feedback loop where we're going to take those and transform them to new costs. So if you remember, originally, every single terminal for the scalars and so on had a cost of 50 because it didn't really know what to assign to them, right? So we were middle of the road 50. Okay, so this has all completed, and then the next cell, we're simply showing you what that pipeline accuracy looks like, right? So this is, by the way, in this cell, Lale can produce an actual Python piece of code that that you can actually import in, you can eval, you know, in your code for that particular pipeline. So, you know, if you want to generate these pipelines and dump them somewhere where you're going to load them at scale in some Python scripts and run them, then you can use Lale for that. And then next to it is the accuracy. So the PCA to logistic regression had an accuracy of 0.9733. There were some with 1, like this one, that were almost perfect, right? So PCA followed by K nearest neighbors. So these are all the 10 ones. Now, we have a problem in mapping back to our domain. And what is the problem? The accuracy scores are for the pipelines. So the accuracy score tells me something about PCA followed by a random forest classifier, or normalizer followed by PCA followed by logistic regression. But in PDDL, the costs are on individual actions. So the question now is, how do I bring that back? How do I now compute new costs, right, for the actions based on the accuracies that I found for the pipelines? And what we did in this particular experiment, there are multiple answers to that, but what we did in this particular walkthrough that we're doing today is something very simple, which is we considered each pipeline to be a set. So essentially think of this pipeline right here as a set of terminals. So it's PCA, random forest classifier. Now, if I had them the other way, it would be the same set, right? So we would have to be careful of that. But right now we're just taking them as sets. And this one is a set formed of normalizer, PCA, logistic regression. And then we have some accuracy scores between 0 and 1. So based on that, we can figure out, you know, PCA contributes to how many pipelines, what is their total accuracy compared to the best accuracy that could be obtained out of all the pipelines that PCA contributes to. Right, and that gives us an idea of how good PCA's contribution is relative to the other. So we can compute a score for each particular element, each particular terminal, each particular sklearn transform or estimator by doing this kind of set mapping. So you have the sets mapped to the accuracy scores, and then we figure out for each element of the set based on how many sets it's in and what's the total of those accuracies relative to the best accuracy that you could obtain in all those sets. And then we compute a score for that particular element, its contribution, essentially. So that's exactly what we do in the next cell. We call a function for this, and the function is free for you to inspect. Actually, I think I have it in, well, I don't have it open right now, but you can inspect it from GitHub. So this function essentially says, well, now that I have all these accuracies, I'm going to send them back as feedback into our little pipeline optimizer, and that will compute new costs for these particular elements of the grammar. And by the way, we're displaying elements that are syntactic elements as well. And for those, we always assign a cost of 0 because those will appear everywhere and they don't have any special semantic meaning. But one thing that we can see through here, well, PCA is on everything. So, but really not everything is perfect, right? So compared to, if you think that PCA is in everything, you know, overall it gets a cost of 77 because not everything is perfect. So from min accuracy to max accuracy, which was 1, you know, we're kind of overall on average, we're 77% of the way. From the minimal accuracy in these pipelines, which I don't know, I think it was this one maybe, or 0.94, I think it, no, 0.9333 is the small. So from between 0.9333 to 1, we're kind of on average 77% of the way with accuracy over all of the things that PCA belongs to. And again, PCA in this case is in all 10 of them. But we can see some differences in the others. So for instance, Gaussian, not very good, right? On the other hand, K nearest neighbor classifier, very good. So low cost is good, high cost is not good. Remember, the planner chooses the top K plans that optimize for costs. So it's trying to minimize costs. So in this case, we assign low scores to the things that were in good pipelines and higher cost to things that were in worse pipelines. So high cost is bad, small cost is good. So in this case, for instance, k-nearest neighbor classifier does much better than the Gaussian NB, right? So what we'd like to see now is if we invoke the planners again with the same argument, so the same number of pipelines and the same constraints. So again, PCA will again be in all of these. We expect to get a different ranking based on cost. I would expect Gaussian to be much lower there. I mean, it will still be there because in the 2 pipeline thing, it will get prioritized over the 3. In the 2 element pipelines, it will get prioritized over the 3 element pipelines. But nevertheless, I would expect it to decrease in importance. And I would expect k-nearest neighbor classifier to increase in importance pretty dramatically. So that's what we do here in this last one. So essentially, we reassign those costs to the domain, and I'm going to show you the domain in a second. And then this is what the plans that we obtained initially when what I showed you earlier. So these were kind of the pipelines, and these were the pipelines after we fed the feedback in. And again, they're organized by optimal cost. So the top one is the one with the optimal cost, and then decreasing a decrease of the cost based in importance. So as you can see, as we predicted, Gaussian NB dropped in importance significantly, where k-nearest neighbors classifier is at the top of the pile right now because it has the smallest cost, right? How is that expressed in the actual PDDL? And that's kind of the last part of the hands-on. So we have here 2 more PDDL files, domain after feedback and problem after feedback, right? So if we look at the problem after feedback, it's going to be very similar to the original problem. So by the way, the original problem was just expressing constraints. The problem after feedback is also expressing very, very similar constraints derived from the grammar, kind of the order of things and so on. But the domain after feedback will have different costs. So if we look, for instance, for, I think, robust scalar. Let's look at robust scalar, for instance. Right, so if we look at the robust scalar action, right now it has a cost of 90. And if we look at it in the original, sorry. Just making sure I'm there. Oh, this one. Oh, hold on. I keep jumping over it. Oh, there we go. So robust scalar, the action on robust scalar had an original cost of 50 in the original domain, right? But after the feedback, its cost increased to 90. And if we match this to what we saw there in the planning thing, right? The robust scalar indeed is, not particularly good for this pipeline case, right? So it cost change, and that cost change essentially caused us to reorder the top K plans. And if you reorder the top K plans, but still keep the same plan, the same number of plans, as you see, you get new plans as well. So for instance, instead of getting PCA robust scalar decision tree classifier, now we're getting the standard scalar, which is slightly better, and the k-neighbors classifier, which again had a smaller cost. It was better. So if you ask for more than 10 plans, you're likely to see a much more diverse set of plans once you reorder the costs. So let me stop right there. This is kind of the end of the hands-on portion, and I have a few more slides to talk about some other applications of this. If there are questions, please do raise your hand or put it in the chat. Okay. If there are no questions, there will be a Q&A section at the end, but feel free to reach us afterwards. You know where to find us. So just to show you that that's not exactly a toy example. So I kind of simplified the example on purpose for this hands-on, but it's not a toy example in the sense that we actually used it for something in practice. So this is an evaluation that we did, and there's a paper published at ICAPS on this exact topic. And what we show is that we compared this with a very strong baseline. And the baseline was some human handcrafted pipeline. So by somebody that was an expert at doing these things, right? So chains of 2 or 3 of these transformers and the estimators that were handcrafted for the particular problems. And what we showed there, which we think is an important example, is that we are able to match the top accuracy in the vast majority of cases. And in some cases, we actually got there faster. So we converged faster to the top accuracy. So you can see the handcrafted ones are red and blue in everything. And the other ones are kind of yellow and red. So you're going to see in some the blue and green converge, relatively fast. But in some of them, the red and yellow, which are the ones that use planning, and the red didn't use the feedback loop, but the yellow used the feedback loop, this feedback loop that I showed. We are essentially matching the same top accuracy for handcrafted pipelines. So at least for some sample spaces of machine learning problems, you don't really need experts necessarily to handcraft these pipelines. Sometimes you can find them and you can optimize parameters accordingly and converge faster to the best pipeline available through this kind of automated exploration. So I wanted to talk about 4 more applications, and 2 of them are related to this. So where we use planning. One of the early applications of this, the automated analytics composer, which I was a part of as well, it was to do the same, but before machine learning frameworks were there. So in this case, we are composing individual analytics, call them models, call them whatever you want, but that were built on various big data systems. So things like streaming systems, you had like the streaming operators that we were composing, or MapReduce components that were running on Hadoop, essentially. And we are composing them into streams, and some of these streams are cross-platform. So you're doing some training on Hadoop, and then you are kind of dumping the model and then running it in a streaming fashion to score. And all of this was done without the actual end users knowing how to put this together in a language or kind of engineer the data communication pipelines between them. And this was a big gain because scaling the number of people that have the technical expertise to build this and lowering the time taken to build all these complex pipelines is always a win. It's a factor. It's a cost improvement factor essentially. Now we took that idea and then we applied it to data science when data science became data science. And we call this project CADS, but it was essentially what you've seen with a slightly different flavor, where you had kind of the individual pieces already kind of pre-evaluated, or you had a framework that would pre-evaluate them on benchmark data sets. And then you had machine learning to automatically determine the best choice of model for supervised analysis. And then we would bring in the composer part via planning, which would take all these pieces that were pre-annotated and they had scores assigned to them. And we would take in the constraints imposed by the cognitive assistant for data science that would kind of pick the constraints, what models you want in what combinations. And then we would basically create a data science pipeline, a much more complex one that I've shown you, obviously, but of the same flavor. So this was coupling kind of symbolic and AI and ML together in one system. Shirin, I believe, talked about this in the medical domain. So hypothesis exploration, right? Hypothesis generation and exploration. And we did this in the medical domain, like Shirin described. That was a very important application, but I also did it in the cybersecurity domain, where we wanted to predict machines that would contact malware domains ahead of time. And essentially you would see so obviously this is a problem with a lot of ambiguity of observations. as well as missing observations, because at that time we had a tap on a very large corporate network. So we couldn't capture everything, we couldn't analyze everything very deeply. So the observations that you were getting were sometimes unreliable, sometimes missing, and so on and so forth. But we had a model of what it means for a host to get infected by malware, and then how it contacts a command and control domain, and what the results are of that. And there were some impressive results that I'm going to talk about in 2 slides in the summary. But primarily that we were able to detect a lot of these hosts between the time they got infected and before they contacted their first site on any of the, like the Google blacklist or any of these domains that are known to be malware. So that was an important result. And finally, with the scenario planning advisor, you've already heard it spoken about. We had similar problems with the application domain is not the planning domain, right? Which is the application domain was essentially, risk factors and causal relationships and between those and the intensity of those causal relationships, and how do you map all of this into a planning domain and then be able to kind of recognize based on these observations, these plans, and project them into the future. So what's going to happen next? But in all of these, you're probably going to say the same theme, which is you have an application domain. It sounds similar to a search problem that you can solve with planning, especially if you have constraints or domain knowledge that you want to embed, or you don't have enough data to learn from it. And then, so in this example, for instance, an example is like black swan events, right? You don't really have data for those, but you can still have a person imagine them, like pandemics before they happen. So if you don't have data or have any of these conditions, you have something that looks like a planning problem, and then you have to do the hard work of translating that application domain to the planning problem, apply one or more planning formalisms to it to get plans, and then post-process the plans back into your application domain. So in this case, we had to present business domain experts with scenarios that they would understand, not with plans. And this is very much what I've shown you today, where we started with a grammar, we turned it to HTN, PDDL. We got plans out of it, which were somewhat human understandable if you look to them carefully and you know the grammar, and then get back actual ML pipelines. So again and again, it was the same kind of framework. So I'm gonna stop for 10 seconds, see if there are any questions. If not, we have a few more slides for the summary. And then there's another slide for Q&A at the end, if you found any questions in the meantime. Okay, moving on. So we just have 3 slides that summarize what you've seen, what the good news are, and where we think there's room for improvement. So you got an idea of what AI planning is and what the theory of AI planning is, but there are so many formalisms and planners and models and languages, and for a very good reason, which is the search problems they solve are sometimes very, very different. But you also have frameworks like PDDL or HTN that are going to bring a lot of these formalisms together so we can build one set of tools on top of them. You heard Shirin talk in detail about various modeling problems that we had, and you heard me emphasize the same thing again, which is modeling is key there. And we think one of the areas for improvement is it doesn't scale if you need a planning expert every time you need to go from an application domain to a planning domain, or every time you have a change in the application domain and you need a change in the planning domain. So modeling is a key part of it. So the knowledge engineering part where you take the domain knowledge and you take the planning knowledge that the expert has and transform the application domain into the planning domain. How do you transform it? What transformations are possible? What approaches we took? So you saw a long history of that through applications. And finally, you've just seen kind of a hands-on application of that to ML pipeline exploration. And we used a bunch of these transformations and tools that we described earlier. So that's what you've seen. Now, what's the good news and what can we work on? So the good news is planning can solve some really hard problems. I've seen that throughout the last decade. So just 3 examples of this that we talked about and some references for them in case you want to look at the papers and the actual results. Right, the ML pipeline exploration, we matched the handcrafted pipeline accuracy with a very simple grammar. So, you know, this was kind of, we tried it and we matched what experts were doing, what an expert was doing almost immediately. There's the hypothesis generation and the analytic automation part. So in cyber, for instance, Shirin talked about the healthcare case, but in cyber, for instance, we are able to predict which host will contact the malware domain hours ahead before this happened. And this was before most, you know, neural models were in place. So we didn't compare against any of these, but this was kind of state of the art at the time. And then in scenario planning, we can generate scenarios dramatically faster than any human expert, but both in terms of scenarios and in terms of underlying, you know, knowledge domains. We can extract this from documents faster than any expert. And after we pass the first scenario, which we pass the model generation part, then we can generate scenarios really, really fast, faster than any team of experts could do. So some really hard, real applications that can be solved with planning, assuming you go through these, you know, modeling step, which is always critical. So where can things be improved? As I said, I hinted at this not so subtly many times, but expressing the problems in a formal planning language is definitely a barrier for non-experts, right? So we need better knowledge engineering tools that would allow you to somehow declaratively go through from the application domain to the planning domain easier. And there has been work on that. So if I remember correctly, Michael did some work on black box planning where you were expressing essentially your domain as Java classes, if I remember it correctly, right? So there have been some attempts on that, but some concerted effort in that space would greatly increase the adoption of planning as a tool to solve some of these large search space problems. The other thing that the community has picked up on, and I'm proud to say that the group in IBM of which I was part of for more than a decade, has done was promote this idea that you need multiple plans. You need top K plans. You just don't need the best plan or the fastest plan or any of those, right? So you need multiple plans, and that's natural for people, right? If you ever use Google Maps and you have multiple variants of your plan to get to the airport, you understand why multiple variants are important. There's always domain constraints that you can't easily explain, that you can't easily express formally. So giving people multiple variants and letting them recognize which one is ideal for them is much easier than having them write those constraints formally. Right. So that is key. And luckily enough, the community has picked up on it. So we have some pretty good top K planners right now, some of which we developed, some of which are developed by others. And finally, AI planning is a faster way to prototype than building a custom domain solution. So writing your own algorithm to do search in your own space, right? Translating it to a planning problem and kind of writing the PVDL and trying out planners and figuring out what, you know, possible sets of actions you have is faster than, you know, writing your own algorithm to do the same, but over a custom search space. The problem though is we still are lacking in terms of integrated frameworks and tools that go end to end. So we can rapidly prototype. So I'm thinking of this, you need something like Jupyter notebooks for planning, right? Where I can very easily go from an application domain from with basically zero risk, right? From an application domain to a final result. And obviously you don't run Jupyter notebooks in production on, you know, petabytes of data. But you could, but leaving that aside, it's a very, very extremely good tool for experimentation. And we need something conceptually akin to that, we believe in for the planning world as well. So again, take these as our opinions of where work is needed in this space. And I'm sure there are many, many others, but also take this in the context of the good news. There are a lot of hard problems that are solved with planning, but there are also things that we can work on. And let me stop there and see if there are any final questions that anybody wants to ask.
If you would like to ask questions, but would like us to stop the recording before that, we can do it. think we can stop the recording at this point.
Yes, why don't you stop the recording right now?